Hello and welcome. This is day 2 of electron configuration. So we're going to be implementing the different rules that we talked about yesterday with the Aufbau principle, with Hund's rule, with Pauli exclusionary principle. Those different rules we're going to be taking a look at when we look at orbital diagrams. And so remember, orbitals are the different shells or shapes, and some of them include S, P, D, and F. And so those different orbitals have different shapes, and we can remember each orbital holds 2 electrons, and each subshell, either the S can hold 1 orbital, the P can hold 3, the D can hold 5, and the F can hold 7. So using that information, we're going to start filling this in. So let's look at calcium. So we have calcium, and let's assume calcium is going to be neutral here. So find calcium on the periodic table. Calcium is number 20. That means it has 20 protons, 20 electrons when it's neutral. On average, it has 20.08 neutrons, but 20 protons, 20 electrons. So let's do the orbital diagram for calcium. So that would be 20 electrons, and assuming like the nucleus is here, the electrons are going to fill in the closest to the nucleus first. So that's going to be the 1s. After that's going to be the 2s. After that's going to be the 2p, 3s, 3p. So basically, least energy, more energy after that. So it takes more energy to be in orbitals that are farther away from the nucleus. But let's go ahead and start drawing these in. It says write out the orbital diagrams for the following elements. And we're going to be showing this with electrons. So we're having 20 electrons, 1 electron spinning up. The other electron, before we can move on to the next orbital, would fill in and go down 2. So that is going to be your second electron. Then you move on to the next orbital, which is 2s, 3, 4. And then remember, using Pauling exclusionary principle and Hund's rule, we don't double up until we get all of these orbitals full of 1 electron. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, and 20. So that's 20 electrons that we have for calcium. That would be the orbital diagram, or where the electrons would occupy in the electron configuration for calcium. So if you're going to write out the electron configuration for calcium, it would be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Sorry, 4s2. That would be electron configuration for calcium. All right, let's look at zinc. So on the periodic table, we can find zinc, and zinc has 30 electrons when it's neutral because it has 30 protons. So we have 30 protons, 30 electrons when it's neutral. I'm going to go ahead and write that in, 30 electrons. And then once again, we're going to start filling using the Aufbau principle. We fill up, we build up from this section from the left to the right. And you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, and 30. That would be the electron configuration for zinc. I'm not going to do cesium. I want you guys to try it on your own. So I want you guys to find your periodic table, find the number of protons, which would be the same number of electrons when the atom is neutral, and you can go ahead and fill that in yourself. So let's move this. We're going to continue on. So if we're looking at this, electron configurations for ions. So remember, ions are when you don't have the same number of electrons and protons. When an atom loses or gains electrons, it becomes an ion. The loss or gain of electrons will alter its electron configuration. Electron configurations examples below. So aluminum, we can find aluminum here on the periodic table is number 13. It would have 13 electrons when the atom is neutral. So we can just start writing this out. 1s2, 2s2. So it'd be kind of like working our way across from left to right. Then this is the 2p, this is the 3s, and this is 3p. So we get to 2p6, 3s2, 3p1. So if you're looking at this, we have our aluminum has 13 electrons. When it becomes an ion, it becomes a +3. So remember, when you have a +3, that means you're going to have 13 positive protons, and that means you would have, in order to have that +3, you're going to have 10 negative electrons. So now we're going to write the electron configuration for what would look like 10 electrons, which actually look like neon. So 1s2, 2s2, 2p6. The electron configuration for aluminum with a +3 ion looks just like the electron configuration for an atom of neon. So if I ask you what is the electron configuration for neon, it would be the same as that. So I'll write down the electron configuration for sulfur, and let's see if you guys can get the sulfur ions. So here's sulfur. Down there you'd have 1s2, 2s2. So if you're kind of working our way across 1s2, 2s2, 2p6, 3s2, 3p1, 2, 3, 4. So it ended in 3p4. So 2p6, 3s2, 3p4. And then I want you guys to try to guess, or not guess, but use your information you've figured out so far and determine the electron configuration for sulfur with a -2 charge. So when it becomes an ion, you can go ahead and write that in, all right? So continuing on, let's just keep going down further and further. It says write out the orbital diagram for the following. So let me get there. So here's the orbital diagram for a couple more elements. We have copper. I'll do copper and then you guys can do chromium. So copper has 29 electrons. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29. That's 29 electrons. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d9. I'll let you guys do chromium. You can figure that out. And it says, wait, what? That's exceptional. Write out your own rule based on the two examples. So if you're looking at this, you're like, what in the world? Chromium. Actually, the interesting thing here, so if we go back to, I was not telling the truth here with what happens with copper. So most elements do that kind of just filling in normally, but copper is a little interesting. So we could fill it in like this. It has one orbital that has only one electron in the d orbital. What happens, because copper is so exceptional, is this s electron here will actually move to form this d orbital, and so all your d's are going to be completely filled. And what's going to be left over is one s orbital, or this 4s with only one electron. And this basically is just because it's less energy to be here than it is here. So the copper is going to have that one electron in the 4s, and that's exceptional because that's not normal. And so what happens, lots of times we see copper with a +1 charge, because when it forms an ion with something, it loses that electron, and then it has all of its electron orbitals filled, which we'll talk about in the future what is the purpose of that. So let me do chromium with you. So chromium is actually number 24. 24 electrons. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. So I don't know, you may see this coming. In the same way, you have this one orbital and the 3D is empty. We're going to take one of these electrons here from this 4s, and we're going to move it and put it right there. And so that electron is going to fill in that one orbital. And it's kind of going against the couple rules that we talked about so far, where it says you fill it up before you go to the next section. But now if you look at it, these all have one electron in it, and that's going to be better for this chromium than having two over here. So now, once again, chromium can have that same kind of thing where it could lose this one electron right here and form a +1 charge. So that's just chromium and chromium and copper are kind of exceptional in that sense. It says white, what? That's exceptional. Write out your own rule based on the two examples. So I want you guys to maybe write out a rule that says something about electrons from the S filling the D's first, rather than the 4s filling first because of the D. So something about that. And last thing for today is this idea of shorthand or noble gas configuration. So each element's configuration builds on the previous element's configuration, as we noted. We can save time and space by abbreviating some of the previous element's electron configurations. To do that, we use the configuration of the noble gas that comes before our element by placing a symbol in brackets. And so noble gases are these whole family over here. So we're going to write out the noble gas configuration for strontium. So strontium is Sr, and Sr is number 38. So you may look at that and go, oh man, it's 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2. Ay. Well, this whole idea of the noble gas configuration is you can go from strontium, go up one, and over here we're going to look at krypton. So krypton's electron configuration is the same as writing all of this. This is the electron configuration for krypton. So I'm going to take this, I'm going to get rid of it, I'm going to write krypton in brackets. So basically I'm just writing krypton plus 5s2. So what am I saying here is strontium, the electron configuration for strontium is just like krypton and this. So if I was to do another example like barium, so barium's electron configuration would be, if you go up and over to the noble gas right here, it's like xenon plus 6s2. So hopefully that was helpful. Get that all finished up, turned in, and